Dear students, today we are going to start our fourth unit, Work, Energy and Power. You might have come across these terms often in our day-to-day life. We are using the term work in every context of our daily life. Whatever we do, whatever the activity we perform, we used to call it work. Work in physics is entirely different from the regular terminologies what we use. What is work done in physics? When a force is said to act on a body, then the force acting on the body displaces it. This is called work done. So force acting on a body makes the body to undergo a displacement. If it happens, then a work is said to be done on the body. In order to do work, we need energy. In order to do work, we need energy. What is energy here? Energy is the ability or capacity to do work. Energy is the ability or capacity to do work. So, we can say here, work is the product of force under displacement, we can say simply, or otherwise it is the displacement made by the body when a force acts on it. And what is energy? What is energy? And energy is required to do this work. See the statement. There is a link between these terms. In order to perform this work, we need energy. So, energy can be defined as the ability or capacity to do work. There are different forms of energy which we used to speak out. One is mechanical energy, electrical energy, then light energy, heat energy, nuclear energy, and so on. It goes on. Whenever you are asked in your lower sections that what is sound, you used to say sound is a form of energy. What is light? Light is a form of energy. For all the terms you use in physics, you used to say it is a form of energy. It is a form of energy. So here we are speaking about energy. There are different types of energy. Mainly we are going to focus on mechanical energy in this particular chapter. We are going to speak about mechanical energy. Mechanical energy has two types. One is kinetic energy and another one potential energy. So we are going to speak about kinetic energy and potential energy. In turn, we are going to speak about mechanical energy. As a sequence of, in the sequence of this discussion, we are going to speak about another term called power. Generally, we used to say it's power, but colloquially we used to speak term this as power. What is power? It is the rate of doing work, or it is the rate at which energy is delivered. So power is rate of doing work or rate at which the energy is delivered. We can say power is equal to work done by time taken. Why am I writing this as work done by time taken? Is work done and energy are the same? Of course, yes. Work done and energy are the same. That is why they possess same dimensions as well as same units. Because we are saying force acting on the body displaces the body so that a work is done on the body. In order to do that work, some amount of energy is required. And the ability or capacity to do the work is called energy. So both are one and the same. We are speaking about the capacity. We are speaking about the capacity. I can give you a simple explanation or example to understand what is work, what is energy, and what is power. With a simple example, we can discuss all the three. So, how will you define power? Power is work done by time taken. It is work done divided by time taken. And here you can say power and time taken are inversely proportional. One thing you have to understand, power, greater power doesn't mean that it is greater amount of work done. That is different. That is this second idea. But thing is that what exactly power is? It is the work performed in a given duration. Work performed in a given duration. That's why we used to call rate of doing work. Anything that happens in a duration, in a time interval is called rate of. So power is work done divided by time taken. Suppose if you say a cricketer is hitting a ball, he gave a powerful hit or a powerful hit here refers to the force acting on the body which displaces the body within a very shorter interval of time, within a very shorter duration of time. That means that the power of the power delivered by him is more. Power delivered by him is more. So we can say a powerful hit or a powerful stroke here refers to a powerful hit made by the cricketer on the ball within a very short interval of time. So powerful hit doesn't mean that you are applying more amount of force, something like that. No, it happens in a very short duration. So in this chapter, we are going to understand what exactly work, energy and power is. So how will you define work? It is the force acting on a body. When this force displaces the body, then we can say work is said to be done on the body. Second thing, power means energy. What is energy? It is the ability or it is the capacity to do work. Ability to do work or capacity to do work is called energy. And then the rate of doing work is called power, or the rate at which the energy is delivered is called power. Rate of doing work is called power. Rate at which energy is delivered is called power. So we can define in both ways. So energy by time taken or work done by time taken is power. Both are one and the same. Now, I can give you a simple example here. Let us consider a stone over here. You are applying a force F so that the stone is displaced through a distance, let us say ds. So a work is said to be done on the stone. A work is said to be done on the stone. So work done is nothing but the product of force and displacement. Now, what is energy here? It is the ability to do work. The fellow who is applying the force on the stone does not make the stone to displace through this particular distance. Then he has no such ability to make the body to move from one place to another. So he has no such capacity. So he has no energy. We used to say he has no energy. If the person who is applying the force can able to move or able to push the stone and he can able to displace it through a distance ds, then simply you can say he has enough amount of energy. He is capable of doing the work. If he is capable of doing the work, then he can say he has the required amount of energy. Fine. What is power here? A fellow A is displacing this stone by applying a force F through this distance ds in a time interval, let us say 5 seconds. 5 seconds. Another person B is applying a force F on the stone and he is also displacing it through a distance ds, but it happens in a time duration, let us say 8 seconds or 10 seconds, whatever. There is a time difference between these two. Then we can say, who is powerful? The fellow who did the work within a very short interval of time is said to be more powerful than the other. So A is powerful than B. A is powerful than B because he did the work in a very shorter duration. You can also understand the same fundamental in a different format. You consider A is doing the work on the stone in displacing it through some distance ds. B is also doing work on the stone in displacing the stone through a distance ds. Both of them are doing the same, both of them are doing the work in the same time interval, let us say 5 seconds. If one is displacing through a distance ds up to this point, let us say I can mark, let us say some 5 meter. Another fellow is displacing the same stone through a distance of 7 meters in the same time interval. Here time interval is same. Let us say the force applied is also the same. Force applied is also the same. Both are applying the same amount of force. If one is capable of displacing it through a distance 5 meter and another person is displacing it through a distance of 7 meter in the same time duration, then we can say time is same. Time is same. Work done is force into displacement. Same amount of force is applied. Since the displacement made by first person is less, power is less. Displacement made by the second person is more, so power is more. So we can explain the power in terms of force applied, in terms of displacement, in terms of time taken. Generally, we used to speak in this order. As work done is considered, same amount of work is considered, then power depends upon time taken. Lesser the time in which the work is performed, more is the power. More the time in which the same work is performed, lesser is the power. So, what is work done? It is simply the force acting on the body which makes the body to undergo a displacement. This is called work. What is energy? It is the capacity or ability to do work. What is power? It is the rate of doing work or the rate at which the energy is delivered. Rate at which the energy is delivered. This is called power. We are going to speak about work first, and then in the next sessions we will be discussing about energy and power. We shall now discuss about work. Let us say a force, a vector is acting on a body, and we can say, instead of showing like this, a force F is acting on the body. It displaces the body through a distance, let us say dr vector. This is the displacement made. And the angle between the force and the displacement is theta. Then, mathematically, the work done can be represented as W equals F vector dot dr vector. And we can say here, a dot product of two vectors, a scalar product of two vectors is a scalar. So, I can say work done is a scalar quantity. Work done is a scalar quantity. What is the unit of work done? It is the product of force and the displacement. Force has got the unit Newton, displacement has got the unit meter. So, work done has got the unit Newton meter. Or, in terms of SI unit, we can say it is joule. Work done has got these units, either joule or in terms of Newton meter. We can represent it as Newton meter. Then, what is the dimensional formula for work done? Dimensional formula for work done can be calculated like this: F into dr. I'm just taking it as F into dr simply, or otherwise F vector dot dr vector, you just take it as it is. Force has got the dimension mLt power minus 2 because it's the product of mass into acceleration. Mass is m, acceleration is Lt power minus 2. So mLt power minus 2 is force, and the displacement has got the dimension L. So we can say the dimension of work done is mL square t power minus 2. mL square t power minus 2. So, work done is a scalar quantity. Work done is the product of two vectors, F vector dot dr vector, a dot product or scalar product. The dot product of these two vectors is a scalar, so work done is a scalar quantity. Its unit is Newton meter or joule, and its dimensional formula is mL square t power minus 2. mL square t power minus 2. This can be understood with a simple diagram, what you usually know for the dot product of two vectors. I can say displacement dr is along this particular direction. Force is acting along this direction. And we can say theta is the angle made between force and displacement. I can resolve this force into two components. One is F sin theta, a vertical component, and F cos theta, the horizontal component. Then we can say here, this instead of vectors, I can simply take F and dr, so that the understanding will be simple. So what is the work done along this particular direction? We can say W is equal to F cos theta into dr. F cos theta into dr. Or otherwise, F cos theta into dr. Both are one and the same. Simply F dr cos theta. If the displacement is S, this is a smaller displacement dr. Total displacement is S, I can write W equals Fs cos theta in general. W equals Fs cos theta. This is the magnitude of work done. Work done has only magnitude. There is no specific direction for work done. Work done is a scalar quantity, so it has only magnitude, and its magnitude can be calculated using this expression Fs cos theta. W equals Fs cos theta. It has no direction. If you are applying a force F, the F sin theta component balances the weight of the object. F cos theta component displaces it along this particular direction. So work done is taking place along this direction. So you can say F cos theta into dr. So the work done on the body depends upon three factors. One, the force acting on the body. Two, the displacement as r dr, whatever the displacement is represented, we can take. So force F, displacement S, and theta, the angle between the force and displacement on the body. Force and displacement are making some angle theta, and this theta is also important in determining the value of work done. This can be consolidated separately. Now, we can say work done depends upon force, displacement, and angle theta. We can go one by one. When do we say a work is said to be done? When do we say a work is not done? Let us say, if the force acting on the body is 0, then what do you say? Work done is 0. When there is no displacement produced in the body by the application of force, then also the work done is 0. And whatever the values are 0 for theta, then also the work done will be 0. We can go one by one. Let us say, if the force F acting on the body is 0, then work done is said to be 0. Let us consider a smooth horizontal surface. A body is sliding over, or otherwise I can say rolling over the surface. It moves along this particular direction. The body is undergoing a displacement now. But there is no force acting on the body. As I told you, there is no friction. It is a smooth, horizontal, frictionless surface. So even no frictional force is acting on the body. Small f is also 0. Frictional force is also 0. Total force in general is 0. So work done is 0. This is for an ideal situation, because friction always comes into play when objects move over any particular surface. Work done is 0 because frictional force is 0. As frictional force is 0, work done is 0. Since there is no frictional force acting on the body, rolling body, work done is said to be 0. So if force is 0, work done is 0. If if a table or a ball is rolling over a surface, there is no frictional force acting on the ball, but the ball is undergoing a displacement, then we can simply say no work is said to be done on the ball, as long as there is no frictional force or no external force acting on the body. This is one particular case. So when F is equal to 0, work done is 0. Second case, when displacement dr or S is 0, then also work done is 0. So simply from this expression I can say, when force is 0, work done is 0. When displacement is 0, work done is 0. And depending upon the value of theta, what are the angles for which the cosine value of this theta is 0? For that also work done will be 0. We are discussing about that only. So displacement is 0, work done is 0. For example, you are pushing a wall. The wall does not move, but you are applying a force. The wall remains rigid and it stands still. So what is the amount of work done by you? 0. Though you are doing, you mean generally, in a context you used to say that I am pushing the wall, I am doing some work. No, not exactly. In physics terminologies, work done is 0 as there is no displacement. If displacement is not there, work done is not there. Work done will be 0. Then, work done will be 0 when the angle between theta, between force and displacement is 90 degrees. When the angle theta is 90 degrees between the force and displacement, then also we can say work done is 0. For example, you are carrying a bucket full of water and you are walking on a pavement. Then, what is the amount of work done? You are holding a bucket. You may say that you are doing a work, but actually not. In physics terminology, you are not doing any work. Suppose if some motor or a water pump got repaired. So you are fetching water from a well. You are taking 10 to 12 buckets of water and filling up a pit. Then you may say that to your mom or dad that you did some work. But in physics terminologies, if they know physics, then they will say simply, you did no work. Why? Thing is simple. You are carrying a bucket full of water. Water whose weight is acting vertically downwards, but your displacement is taking place horizontally. So I can say, if a person lifts a bucket full of water, and he is moving in the horizontal direction, the weight mg will be acting in the downward direction. The angle between the displacement and the force is equal to 90 degree. As per the equation, W equals F dr or ds, whatever, dr cos theta. Here theta is 90, cos 90 is 0, so work done is 0. Work done is 0. So simply we can say, you may take a heavy object and you are carrying it over your head and you are walking for miles together, then also work done is 0. Why? Simply you are holding the luggage or weight over your head. You are moving horizontally, but the weight of the object acts vertically downwards. The angle between the displacement and the force acting is 90 degree. So work done is 0. You can speak about other examples also. For example, a centripetal force. If any object moves in a circular path, then it experiences a centripetal force, as you know, an object of mass m. It is acted upon by a force we used to call centripetal force. Centripetal force always acts towards the center, and the displacement at this particular point is along this direction. If it comes to this particular point, then it displaces along this direction. So we can say the angle made between the centripetal force and the displacement is 90 degree here. Then we can say the centripetal force acting on the body, which is undergoing a circular motion, does no work on the body. So work done is 0 once again, because theta is 90 between centripetal force and the displacement. This is applicable in most of the cases. This idea, this fundamental is used in most of the cases, which you will come across in physics. So since the angle between the centripetal force and displacement is 90 degree, the work done is 0. So we can go on with so many number of examples like this to explain about the work done, which is 0 in 3 different cases. When force is 0, work done is 0. When there is no displacement, then also work done is 0. When the angle between the force and displacement is 90 degree, then also work done is 0. We can say work done depends upon the values of force, displacement, and the angle theta between the force and the displacement. We can consolidate the nature and amount of work done by the force acting on the body depending upon the angle theta. We can consolidate, we can give it as a table so that you can understand very clearly. When do we say force is maximum, and when do we say force is minimum, 0, and when do we say force is negative? You may wonder, I am speaking force is positive maximum, force is 0, force is negative. You may wonder whether work done can be obtained in a negative form, or whether you can say work done is negative. Of course, yes, work done is negative. In which cases you can say work done is negative. There are so many examples with which we can speak about negative work done. For example, you are playing football. You are a goalkeeper. Someone is hitting the ball towards the goal post. Then you are catching the ball by applying a force F in a direction opposite to that of the displacement of the ball. Ball will be trying to move in the inward direction. You will be applying a force in the outward direction, and you will be applying the force exactly opposite to that of the displacement of the ball till the ball comes to rest in your hand. Till the ball comes to rest in your hand. In this particular case, force and displacement are acting exactly in the opposite directions. So what is the angle made between force and displacement? 180 degree. What is cos 180? Minus 1. So F dr cos theta, theta is 180, cos 180 is minus 1. So work done is W equals minus of F dot dr. Simple. Work done is negative. Work done is negative. We can go with another example also. A box is placed over the surface. You are lifting it in the upward direction. A bucket full of water is there. You are lifting it in the upward direction. Weight of the object acts in the downward direction. Displacement of the bucket is taking place in the upward direction. What is the angle between the force and the displacement? I can show you with a diagram also. A bucket is there. A bucket is there, which is filled with water. Its weight is acting in the downward direction. You are lifting it in the upward direction, so it undergoes a displacement, let us say dr. Force and the displacement are at an angle of 180 degree, then we can say work done is W equals Fs cos theta. Theta is 180, cos 180 is minus 1, so W equals minus of F dot S. So work done is negative. Work done is negative. So when force and displacement are acting exactly in the opposite directions, in such cases work done is negative, not zero. So there are all the vector quantities will have both will have positive, zero and negative values. But scalar quantities do not possess positive, negative and zero values. There are very few quantities. One such quantity is work done. Work done may be either positive or negative or zero. So negative work done is also there. Negative speed we cannot say, but negative work done, and that is also a scalar quantity, we cannot say, but negative work done is there. How? We can simply say whenever and wherever you are getting the force and the displacement in the exact opposite directions, there you can say work done is negative. You are going through a lift, the weight of the lift and your body acts vertically downwards, but the displacement of lift and you are in the upward direction, then what is the amount of work done on your body? Negative. Like this, you can go on with so many number of examples which explains about negative work done. Now we can consolidate the table for the different angles theta and the corresponding amount of work done. We shall now speak about the different angles and the nature of work that has been performed on the body. Let us say angle theta equals 0. What is cos 0? 1. So what is the amount of work done? Since we are getting a positive value, I can say it is positive work done and maximum. Why do I say that this is maximum? Because the maximum value of cos is 1. This could be the, or this will be the maximum value of work that has been performed by the application of force and the displacement made in the body. So as we are getting 1 for cos theta, work done is maximum. And as this is a positive numerical, we are saying work done is positive. Then if theta is greater than 0 but less than 90 degree, so we can say an acute angle, whatever the angle between 0 and 90, that doesn't matter. So for cos 0 it is 1, for cos 90 it is 0. So the value of cos theta lies between 1 and 0, or I can say it is 0, greater than 0 but less than 1. This could be the right way of writing the value of cos theta. Cos theta is greater than 0 but less than 1. So it lies between 0 and 1 depending upon the value of theta. Here also we can say the work done is positive, but we cannot say it is maximum. So it lies between 0 and maximum. Then if theta equals 90 degree at right angles, cos 90 is 0. So work done is 0. Cos 90 is 0. As theta is 0, theta is 90, cos of 90 is 0, so work done is 0. Then theta greater than 90 degree, less than 180 degree, means theta lies between 90 and 180, obtuse angle. So where we have to mark this theta, that is important. You have to remember this. dr vector along this direction, f vector is along this direction. The theta is the angle made between f and dr. Here you can say theta is 0, means force and displacement are acting along the same direction. That is very important. So I can show it with the diagram also. F vector and dr vector are acting along the same direction. Here f vector and dr vector are acting by making some angle theta between this 90 and 0. This is angle 0. If force lies along this direction, 0. Comes like this, then 90 degree. Then force and displacement are at right angles. F vector, dr vector, angle is 90 degree. So theta is 90 at right angles. So cos 90 is 0, work done is 0. Then for this case, for obtuse angle, I can say here, displacement is along one direction. Force is acting along this particular direction. This angle is theta, which lies between 90 and 180, and not exactly on 90, not on 180, lies between 90 and 180, obtuse angle. So we can say here the cos theta value for 90 it is 0. 0. And for 180 it is minus 1. So cos theta lies between minus 1 and 0. That's the meaning. So it can be a negative value. Work done will be a negative value. Then if theta equals 180 degree, then we can say displacement is in one direction and the force is acting in the opposite direction. Angle between these two is 180 degree. Then cos 180 is minus 1. Then work done will be negative as well as maximum. Negative as well as maximum, because 1 is the maximum value of this cos theta. So this is positive 1, this is negative 1. So this is positive maximum, this one is negative maximum. So depending upon the values of theta, work done varies like this. Not only for this angle, theta equals 0, theta lies between 0 and 90, theta equals 90, theta lies between 90 and 180, theta equals 180. For other angles also, you can easily determine the value of work done, as you know very well. If you know the values of cos theta, then you can easily determine the value of work done on the body. As the formula for work done is W equals FdR cos theta, FdS cos theta, Fs cos theta. Displacement can be represented in different terms, dr, ds, s, whatever. So based upon the value of theta, as we saw, depending upon the magnitude of force, work is said to be done. Depending upon the value of displacement, you can speak about the work done. Depending upon the value of angle theta between the force and displacement, you can speak about the work done. This is a simple table which will explain you about the amount of work done. We shall see a problem related to this. W equals FdR cos theta. A box is pulled with a force of 25 Newton to produce a displacement of 15 meter. If the angle between the force and the displacement is 30 degree, find the work done by the force. This is the question. So, what is given? A force is acting on a body whose value is 25 Newton and displacement dr is 15 meter. The angle made between this force and displacement is 30 degree and you are asked to calculate the work done. Work done W is equal to FdR cos theta. Force is 25 Newton. Displacement is 15 meter. And the cos of theta, cos 30 degree. So 25 into 15 into cos 30 is root 3 divided by 2. On simplification, you can say you will get 324.76 joule. This is simple. If you calculate the amount of work done, you will have 324.76 joule. So, if force is known, displacement is known, then angle theta is also given, then we can calculate work done like this. 25 into 15 into cos of 30. Cos 30 is root 3 by 2. Then you can calculate the value here. Simple. In this way, you can go on doing so many number of example problems so that you can understand what exactly work done is. And you need to know the values of these angles and the corresponding values of work done also. Thank you.